Hello and good evening, ladies and gentlemen. Let me welcome you in our stream on Science On platform. My name is Silva and I will guide you through this evening. As you can see or hear, this stream will be held in English because it's an international one, and therefore we have invited some very interesting guests from abroad, from all over the world. But before we get into introduction of our guests, let me kindly express my appreciation and big thanks to Mojmír Grammar School in Brno, Czech Republic, which always gives us a place and a space to make our studio. So again, big thanks to this grammar school. Okay, and let's jump into the introduction of our guests. As I said before, this is an international one, and so therefore we will invite 3 out of 6 continents this evening. So who will be our first guest? As first, it will be Carlos from Spain. Hello, Carlos. How are you?
Hi, how are you doing?
We are very happy to have you here. So what will be your experiment about?
So I will give a talk about some research that we performed some years ago in collaboration with Oxford and the University of Rome about how to freeze in carbonite. Okay, thank you very much. So we are very looking forward to seeing your presentation. See you then. Thank you. Okay, and the second one is Mark. Hi, Mark. How are you?
Good, thank you.
Thank you. This is not your first time here with us, so we are very happy to have you here again. And just tell me very briefly, what is your experiment about?
I'm going to change copper into gold.
Oh, it sounds very good.
Yeah, I know.
So
I'm a rich man.
Yeah. So we will see how this will be going, yeah? Okay, so bye.
Bye-bye.
Okay, and now we are moving to Sobit. Nice to meet you, Sobit.
Hi, nice to meet you.
Can you hear me?
Yes.
Yeah, okay. Sobit is a young guy from Bhutan, so we are very welcome, or we very welcome you from this far. Yeah. So what can we expect from you?
Thank you for this opportunity. My working model is called Mindful Driving, Smart Technology for Safer Roads, which is basically about prevention of road accidents.
Sounds good, yeah. So we are very looking forward to seeing you. So bye.
Yeah. Bye.
See you then. Bye. And now here comes the Stuart, but because he is not able to be here with us online, he recorded his introduction beforehand. So now we will play this record for you.
Hi, I'm Stuart Colhagen and I'm the Science Nomad. I'm delighted to be joining the Science On team today for Science Today. Today, I'm going to be bringing in a demonstration to go and help you see how science sometimes transforms how we look at the world. So I'm looking forward to bringing you that kind of changing mind experience just using some water and some jugs. I'll see you soon.
Okay, and the last one is Adam. Hi, Adam.
Hello.
How are you?
Hello. I'm good. I'm good.
Okay.
Great. Everything is great.
Adam is our guest in almost every stream, so we are very glad to have you here. So what can we suggest from you?
Yeah, I'm the radioactive guy, so we need to talk about radioactivity. And we're gonna make, here in our studio, we're gonna make a radioactive battery.
Oh, real good.
Yeah.
Okay, so thank you very much and see you later.
Yeah, see you.
Bye. Okay, so these are our guests. I really think that you can look forward to seeing our guests. But before we will start, I would like to just highlight the platforms we go from. So it's mainly YouTube, Twitch, and Facebook. So if you are watching us from one of these platforms, just stay tuned and have fun with us. And we would like you to also be very active and interactive. So please, if you have any questions on our guests or comments, just feel free to put them in a chat. Yeah, and then after the presentation, we can discuss with our guests your questions and comments. So please stay tuned and have fun. So again, hi, Carlos.
Hi.
Can you hear me?
Perfectly.
Yeah, okay. So we are very happy to have you here. This is your first time here with us on stream. So how are you feeling?
So I am feeling extremely nervous because I had to buy a lot of things that I didn't knew that even exist. So this lighting stuff, but I am very excited to be presenting what I am going to do.
Okay, okay. And as we talked to each other before, I found out, or you told us that your hobbies, among your hobbies, there is singing. You act like a singer. What can you tell about this?
Well, I'm not a singer. I'm just singing in the choir of the school of my daughter. So today I'm not going to the rehearsal. So I hope that they will allow me to sing anyway.
Okay, okay. And I also find out that you are associated professor at a research group in Barcelona. And so could you tell us what is your research about?
Well, I will tell you some of my research indeed today. Mm-hmm. Okay, I did some research that I did some time ago. And what I love is to study water. So water is absolutely incredible. It has a lot of strange properties. So I love to study water and mix it with some funny things.
And I also found out that you are interested in tardigrades or water bears. What impresses you about these small animals?
But this is going to be a secret until I start my presentation. So they are very special animals. Okay, they are very special animals, and I think we can learn a lot about from them.
Okay. So let's begin, and the floor is yours.
Thank you. Okay, so I don't know if my presentation I can. This is my guy. So I don't know if you know that this guy here. Okay, I have it here. Just he will appear. This guy here does not like very much the rebels. Okay, one of the rebels he was like trying to chase was Han Solo. So finally, this guy managed to chase Han Solo, and the punishment was indeed to make it freeze in carbonate. So this is my companion, Han Solo, and I'm going to explain to you, so if you can now switch again to the presentation, so I'm going to explain to you if this science fiction movie in which you can freeze one person and then unfreeze it, because this is the point. This is to freeze is very easy. The problem is to come to life again is possible or is not possible, or if it has been done before. And the answer is yes. As always, nature has a very intelligent way to act, and here we have the animal that is able to freeze, to stay in a latent way of life, let's say, and when water, when you pour water again to this animal, then this animal comes to life again. And the question is, okay, but we are now talking about Star Wars, okay, so space, and the question now is if this guy is really so tough as you may think, and what do they do to this poor guy? So this poor animal, the tardigrade, they put them into a spacecraft. You can see now this round thing. They put it inside. They launched the spacecraft and they started to make orbits around the Earth, okay? And at some point, the nice guys that were ruling the experiments, they open this container here and they leave the tardigrades just to the conditions of outer space. Of course, we would immediately die. Let's see what happens with the tardigrades. So they close again after 12 days. They close again these doors. They put it in the spacecraft and they make it back the way back to the Earth. Okay. Once in the Earth, they put water on these tardigrades. And now I want to ask you some question. How many percentage of them do you think they came to life again? So you can answer in the chat. No one, 10%, 100%. Wow, this is too tough, I think. Again, 100%. Wow, you are very, very fond of these animals, I tell you. 20%. Okay, a little. This would be really, well, 20%. This is not so bad. 19, okay, almost 20. So if we could 1%. Wow, 1%. 15. Okay, I see then two answers, no? So maybe they are some like a little too much and a little too low. So the answer is that 70% they came back to life and they acted as if nothing happened. Okay, I have to say that the ones that were also exposed to UV, In this case, from 3,000, only 3 survived. Okay, so it seems that UV is too much for them. The radiation is too much for them. So we will know in a talk afterwards. But it seems that low pressure, extremely low pressure indeed, low temperature, and these kind of things, they manage to survive. Okay. Okay. So now, if you can put the presentation again. Okay, excellent. Now, the question is why, because we are scientists, and the question is why. So I cannot answer this directly, because I would like to take you, if I may, in a strange journey about phase transition and the states of matter. Why? You will know shortly. So let's start with solids. What's a solid? Okay, in this case, we can see a wonderful, now that we are approaching Christmas, you can see here a crystal of a snow crystal. Okay, and why is this snow crystal like this? And this snow crystal is like this because the microscopic structure of water is also making this kind of shape. Indeed, I have here one very nice snowflake. Okay, you can see the hexagons. Okay, so what they are doing is that you have a microscopic, microscopic, some, I think 6 waters, 3 waters, I think, no, 6 waters. Okay, so they are forming this hexagon. So they put one hexagon after the other one, after the other one, and after the other one, and so they complete a crystalline structure that we can see with our eyes. That means that indeed the shape of the snowflakes is related to the microscopic structure of water when it's frozen. Okay, okay. And what's this? What has this to do with life? And this is very important, because the problem with this with the solids like this, they are forming this kind of puzzle. Okay, and this puzzle, the problem is that, as you can see here, on when you see a very nice snowflake, I don't know if you see this kind of edges. Okay, so the problem with these edges is that indeed for life, these edges are exactly like this. So the problem with crystalline structures is, for example, the one of water, is that once you freeze water, these crystals, they cut your meat, they cut your flesh, and the problem is that they make they break all the fibers of your I don't know, whatever it's frozen. Normally is this part of the fingers, or maybe it's the nose. Okay, so the problem is that once the flesh is cut, then you cannot recover it. Okay, so, and this is a problem because we have to avoid this. Okay, did you ever see a crystalline growing just in front of your eyes? I see that some of you did, but I will do now this experiment. Okay, I hope that you can see now. This is, it looks like water. Okay, what I am going to do now, indeed, this is not water. This is water with some molecules. Okay, what I am going to do is put here inside this this jar, I'm going to put a crystal. Okay, why? Because if I put a crystal inside this liquid with the molecules, what I am going is to show them a piece of the puzzle so that they can complete the piece of this puzzle. Okay, so if now I take this thing here, okay, this thing here, okay, this is the liquid which is frozen. This is the liquid which is not frozen, and I will put some of no, here. I don't know, illumination is not so good. I don't know if you see them, but ahora. Okay, I don't know if you saw them, but I have a lot of jars, so I will repeat the experiment again. Okay, now at this distance. Okay, where is my, okay, I think I can put it like this. Now, okay, you see now that the crystals are growing. Okay, I don't know if you see. Okay, the crystals now They are growing, so we can do it again. Okay, here in my hand I have some crystals. I put them inside. Okay, now you see the crystals growing downwards. I hope that now you see it. Okay, so now I had a liquid, and if you look here, what I have is a solid. Okay, so this kind of crystallization that we have done here on the fly is very dangerous, because once you have the crystal, all the fibers of your body are broken and then you cannot recover again. Okay, so the question is, then let's go for the liquid. Okay, so we had now the knife. Let's go for the liquid. Okay, this is the solid, the liquid. What's a liquid? I have here the same as before, the pieces as before. I cannot show you the molecules in a liquid, but I can show you this, which is a jar, okay, full of these pieces, which now they are disordered, okay. Here they were ordered, here they are disordered, and that's exactly a liquid. So in a liquid, you have the pieces that are disordered, and this is good because, and that's why this is the foundation of life, because the disorder, okay, allows you not to break, for example, the cell membrane. Okay, so now let's go again. So now liquid means disorder. Excellent. And the nice thing about disorder is that this kind of elements for life, okay, they are like a teddy bear. Indeed, they are like a teddy water bear, because I found this lovely creature, okay, which is a tardigrade, and you can sleep with it, okay, you can do whatever. So this tardigrade is now liquid, so she loves liquids, okay, because liquids do not break the fibers of our body. So I would like to have a liquid, not a solid, which is like a knife, okay. And the question now is, okay, so if we need a solid which is not breaking the fibers, which is not like a knife, can we make a liquid solid? And the answer is that you have probably done it in your kitchen, okay. This is candy, caramel. When you do caramel, you have a liquid, okay, and when you pour it, I don't know if you have ever done it, okay, when you pour it, it flows, and it flows slower and slower and slower until it flows so slowly that it looks like a solid. And then, okay, then we have again this. And the point is that no, you have a solid, but a solid that is disordered. And this is the nice thing about some liquids such as candy, okay. Claro, the problem is I was thinking about making here caramel and with a little I don't know, heater or something, and this was too dangerous. But there's another way, there's another material that behaves a little bit like this, and I don't know if you have ever seen it, okay. This thing here, wait, I know you are only seeing my face doing strange things, and now you will know what's that, okay. This is a mixture, okay. This is a mixture of potato starch, corn starch with water, okay. And I don't know if you see it, okay, but if you don't see it, I will take it out, okay. And in this case, you hear, okay, I don't know if you see it here. It is now behaving just some like a solid. I can mold it, but as soon as I stop doing this, it flows like a liquid. So I don't know if you know this this material. Okay, this is called a non-Newtonian fluid. But the nice thing of this is that depending on how fast you move your hand, is behaving as a liquid or as a solid. Okay, and this is exactly the same what happens with caramel. The nice thing is that with caramel you do it with temperature. Here we do it with our hand, and we can see it live. And now the problem is that I am not able anymore to touch anything. Okay, so I have to wash my hand. Okay. By the way, if you are a teacher, there's a very nice experiment you can do with your students, because this experiment is nice, but it's everything. Okay, it's only nice. But if you put a ruler and you measure the time that the ruler needs to sink in this mixture, you have a calculation of the viscosity of the liquid. So you can take the ruler, you make it sink, you calculate how many time you need to go to sink 2 centimeters, for example, and then you can do it, for example, for different concentrations of water and starch. And you can do a very nice research project with your students. If you are, you can also do it at home, even if you are not a teacher, of course. Okay, so let's continue. Okay, so indeed, you have a lot of these kind of materials which are liquids, but they behave as solids. You have candies, plastic, and of course, you have also glasses. Indeed, these materials, they are called glasses, okay? And this, I am cleaning the table because now it's like full of bad. Okay, now they are called glasses, and then you can find it in a lot of places, for example, in the glasses of a church, okay? Perfecto. So a little bit of disorder is good for life, okay? Water is excellent when it's not frozen. When it's frozen, kills. When it's not frozen, allows life. But the question now is that how do we study the structure? Okay, how do we researchers study the structure? Because the problem is that we cannot use a microscope to study the structure of molecules. Okay, because we don't have microscopes that are so powerful. So what do? We have to use a very special microscope. We use we can use another techniques, but we use neutron cannons. Okay, we must build a cannon which is throwing neutrons. Okay, and because they bounce with the material, the way these neutrons bounce with the material, we can try to learn how is the structure of the material. Okay, the problem is that the cannon cannot be as nice as this one here. Okay, that would be very cheap. The problem is that we need something like this. This is a neutron cannon which is in between Oxford and London. This is the place where we did the experiments. It's called ISIS because of the river, not because of another thing. Okay, and in this case we have done an experiment. You cannot see it, but you see the donut. This is a synchrotron. We didn't do it here. The other thing here is that is indeed in below one of the mountains you can see there. Okay, and if you go into the experimental hall, this is how a neutron cannon looks like. Okay, in this case we have neutrons going everywhere. Okay, and we use them to make them collide with our sample. Okay, and now we are going to do a neutron experiment live, but not with neutrons, because you need a very complicated infrastructure. You can see my tardigrade here from my t-shirt. Excellent. Okay, so how does a neutron experiment work? Okay, so you have the cannon, which is going to be here. Okay, vale. My neutrons are going to be coins. Of course, you can do this experiment at home or with your students if you are a teacher. And our sample is going to be this thing here. Okay, so we put our sample here, and now we throw the neutron, our euro coin, to the sample. Okay, and then we see that here we have one coin ended up here, another one. What I am interested is in the direction. Another one here, another one here, another one here. Okay, I will not repeat the experiment a lot of times because it would be very, very, very long. And one neutron is on the floor. Okay, one neutron here, one neutron here, one neutron here, one neutron here. Okay, but I don't know if you see our results. If we now put here a detector, we will see that all the neutrons are either here or here, and some of them are here. Okay, this is because, of course, of the collision, and because we have very defined shape. If we now take this, okay, and we plot here the amount of neutrons, okay, you will have here a lot of them, and you will have here a lot of them. Okay, if this is a paper and you put it like this, you will have something like this. Okay, so from this peak here would be this one here, and this would be this one here. So from the shape of this curve, we can try to understand which was the shape of the thing we have been studying. I don't know if you understand that the problem is that what we get is this thing here, and what we don't know is the shape of this element. So the problem is that we have to make some tricks to get the shape of the sample from the amount of neutrons that ended up in some directions. Okay, so this is complicated, and it's even more complicated if what I have is a potato. Okay? If I have something which is not ordered, if I have something which has not a well-defined shape, okay, neutrons, okay, some here, some here, so here, 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 again, here, here, now here. So now, I don't know if you see that neutrons can end up in any place here. So when you try to plot this, so this angle, okay, you will have some kind of potato. So here we got, and here we got a potato. Okay, this is ordered, and this is something which has not a well-defined shape. So we can distinguish between these two things with these two shapes, okay, this and this one, well-defined shape, not so well-defined shape, because of the way the neutrons bounce with our sample. Okay, back, high. Okay, so indeed, now I have a question for, this is me. Okay, this is me doing the experiment in the neutron source at ISIS. It was very nice, so I was like saying hello. Okay, and the question is, this is real data. This is you are going to be real scientists because this is real data, and I want you to tell me which one is the ordered, which one is the crystal, which one is this one, and which one is the disordered, which one is this one. Okay, so if you can put the presentation, which one is which one? A, B, which one is the liquid, which one is the crystal? Oh, okay, one liquid, two crystal, disorder A. Wow. So you are really, you can do now neutron experiments. you all know a lot about neutron now. Okay. Yeah. Okay. Excellent. So almost all of you say that A is the liquid. In this is a sugar with water, and B is the crystal. And indeed, this is water that has crystallized. Okay. So excellent. You can now go and do neutron experiments. Okay, so if you can put the presentation again. Okay, this is amorphous, no order, liquid. The down is crystalline, ordered, solid. Okay, for some of you that are a little bit about physics, indeed this is not so simple. Okay, this is a diffraction experiment which was done by Bragg, and we are not going to enter here, but just if you know what I'm talking about, this is diffraction experiment. Okay. Ostras, but I mean, I was talking about water bears. So this is the guy that I was talking about, and then what has this to do with water bears? And it has to do a lot. Okay, so we have done a neutron scattering experiment, not with coins, okay, but with real neutrons, and we have studied the structure of one sugar which is inside the body of the water bears, and this crystal is trialose. Okay, if you see the molecule of trialose, okay, is this thing here. Okay, so we performed this neutron experiment to study how water gathers around this molecule. And this is how water is around trialose. I don't know if you see it. You have the molecule, which has two sides, these two sugars, and you have a scarf, okay? You have a donut around this molecule. I don't know if you see it. This is real data in the sense that it comes from real experiments, okay? So this water is somehow very tight, united very tight to this central part of the molecule, okay? And now what we have done is we have compared it with another sugar, which indeed is not in our water bears, and indeed is in some biological tissues that get damaged with water. That means that I don't know if you have ever forgotten a salad, a leaf of salad in the freezer, and you know how it looks like afterwards. Okay, so this is cellobiose. This is the responsible of having the structure of the leaves, for example. And if you can see now in the PowerPoint presentation, you see that the water is not very tight united to the molecule, but is somehow outside and is in very given positions. Okay, is in some positions of this molecule. What we think is that trialose, the one which is inside the body of our tardigrades, is hiding the water, is not allowing the water to make crystals. And to do that, is making this donut, this scarf around this sugar. In the case of cellobiose, in the case where you have the water which is freezing, okay, what you have is that water is so outside of this molecule that it allows to make crystals. That means that it allows to make the killing knife of crystals, okay? Indeed, somehow it's like, this guy, I don't know how known is it, okay? Water is hidden in the structure of trialose and is not hidden in the structure of cellobiose, okay? Indeed, not only my friend, but a lot of animals are using trialose or glycerol, which has is another story, okay? But the question holds. So we have this guy here, Han Solo, and did we do this with humans? And the answer is yes. We have frozen humans, so we changed. Not we, sorry. One company in the States. Not we don't do that. Okay, and they have taken the bodies of the dead people. They change it by not trialose, but another substance, which is glycerol. Okay, and they freeze them. The problem is that not to freeze them. The problem is when if they can go back to life. But at least with glycerol, you don't have the water making the knives. Okay, what you have is the water bear, teddy bear, soft structure, so it's not killing the fibers of the dead body. Okay, if you see in the figure, you have some small containers. I think you can guess what's in these small containers. Okay, so and as always, research is not done by one person. So here they are some colleagues of the lab I am working, and I acknowledge them to be very nice colleagues and also to help me to do all this research. So me and the water bird want to say goodbye.
So, Carlos, can we see you?
Yeah. Sorry, I thought
you are online. Okay. So, Carlos, it was very amazing presentation from you. I have many questions on you, but maybe I will leave them to our final discussion because we have one question from our audience. So maybe we will put the question from the audience. So what is the source of neutron you use for neutron scattering measurements?
Wow, somebody, okay. So normally we go to ILL, which is a neutron source. This is a nuclear power plant, so it's a little bit more complicated, which is in Grenoble, in France. And another one that we have been using is the one at between London and Oxford. It's called ISIS. Okay, this is the two neutron sources we are using normally.
Okay. And now we have some reaction comments on your presentation. Scientists are happy people. They think about crazy things and they try them too. Is it correct?
You have to be a little bit, yeah. You have to be a little bit crazy to find it very nice to go at 3 o'clock and do a sample change, which this happened to us. No matter how well you plan your experiments, at some point you will have to change your sample at 3 o'clock in the morning.
Yeah, that's true.
Lovely. It's lovely.
Yeah, that's true. And I think it's very lovely from you that we can see that you love it. Yeah, that you live it. So, okay, thank you very much for your presentation and stay with us and we will see you in the final discussion. Yeah? Bye. And now we are flying to Australia to our another guest. So now we have landed to Australia. It was pretty fast flight. And our guest for this stream is Stuart Colhagen. This is a man who from 2017 calls himself as a science nomad. This would be my question on him. What is it about, this nomading? But unluckily, we don't have him online, but he prepared some videos for you and he prepared some experiments. So now we will, and he divided into 3 parts. So now we will we will play the first part of the video and there will be a question. So look properly to have your answers on his question.
What I'm going to demonstrate today is really an example of how sometimes in science we have a question and we get one answer. But sometimes in science, the really big changes in science come from when we make a discovery, someone looks at the world in a very different way. And when that happens, we don't get one answer. We get a whole new perspective on kind of how the world works. And from that, we sometimes start to be able to ask all sorts of many questions and find many, many answers. Like when we broke into the world of quantum science. We didn't just get one answer, we got a whole different way of looking at the world and many questions and many answers. So I'm going to do my best to kind of bring you that experience today, but I'll need you to try and solve some problems for me. So the activity for you to think about during the stream is, I've got 3 containers. This holds 8 litres of water. This holds 5 litres of water. And this holds 3 litres of water. At the moment, we've got 8 litres of water just in the large container. What I want you to think about is how can we get 4 litres accurately in this container and 4 litres in this container, but we have a problem. We've only got markings at 8, 5 and 3 litres. We can't guess. So even though I can see where the water is, I don't know if that's 1 or 2 or 2.5. So if I'm pouring, I really have to pour until either the jug I'm pouring from is empty or I've reached the 5 or the 3. I can't stop in between. I've got to go all the way. They're the only markings I have. So I can pour from the 8 litre into the 5. Trying not to spill any. Science is accurate. Let me see where my 5 litres is. And now with 5 litres in this container, I know I've got 3. So 8 minus 5, 3. But the challenge you need to come up with is, how do I get 4 litres in here and 4 litres in there? So when you have time during the stream, come back and try and solve that problem. We're going to come back, show you one way to solve the problem, but then we're going to show you a whole different way to think about the problem and see how that changes your ideas. We'll see you soon.
Okay, so did you catch it? As you could hear, Stuart has some more solution for us, but before other solutions, we have one question on you from this first part. So maybe we can show you this question: how to achieve 4 litres each in an 8 litre and 5 litre container. So guess, try it at home, and well, we will see next time. And now we will move to Netherlands. So back to Europe. Hi, Mark.
Hello.
Can you hear me? Can you see
Yes.
me?
Yes.
Nice to see you. Nice to see you again. So, how are you enjoying this evening?
It's very nice, very good. Very
Okay.
nice people, very nice topics. So, yes, very good.
Okay. Okay, thank you. So now we are looking forward to your experiment or presentation. But before we get into this, I have a question on you, because I noticed on your social nets that you are doing judo for quite a long time. So maybe I was wondering, how long have you been doing judo? And I also noticed that you have a black belt in this. So can you tell us something about this, about your judo life?
I was starting judo when I was 5 years old, and last week I became 55. So I practice judo now 50 years, and I have the 6th black belt. So that means I do not wear a black belt, but a red-white belt.
And this is possible to have 6 black belts?
Yeah, it's called a 6th dan, and that means the belt isn't black, but has white, red marks on it.
Interesting. I didn't know this. Yeah. And one more question on you. I was wondering what aspects of judo do you use in your everyday life, or does it help you somehow?
Yes, it helps me a lot because judo isn't only a sport, it's a way of life. And for me, what's very important is to get up one more time often than you fall down.
Mm-hmm. Great. This is a great idea. So now let's jump into your experiment, and the floor is yours.
Thank you. I have an experiment where I can show a nice experiment that you can do in school with copper coins, and you can change the color of the copper coins with this experiment. And in this first experiment, I will have a treatment with zinc. And the question that I have with this experiment is, what will be the color of the coin after the treatment with zinc? A, bronze, B, silver, C, gold, D, it remains copper. So now we have to wait for the answers. Alice thinks it will be copper. Karinka, B, silver. C, gold. D. Oh, nice. Oh, for a lot of people, it will be a surprise, I think. Okay, thank you for the answers. We will find out during this experiment. I think there's going to be a little magic now because we will switch to my classroom. I recorded the movie with this experiment because I had a surgery yesterday, so I could not go to my school. So I prepared a film. Alice, can you start film? So, welcome in my classroom, and today I want to speak with you about an alloy. And an alloy is a mixture of metals, and this is an alloy, and this alloy has the name brass. And today I want to demonstrate to you an experiment where we can make our own brass. So, for this experiment we need an evaporation dish, we need a burner, we need sodium hydroxide, zinc powder, water, and something made of copper, and I will use a 5 euro cent coin. Let's start the experiment. First we will put some sodium hydroxide into the evaporation dish. We have to make a concentrated solution, so we use several pellets. Then we will add some zinc powder. And then we will put some water to it. So, to start this reaction, we have to use the burner. So we will make a blue flame and heat the mixture. Meanwhile, we can use the coin and put it into the mixture. And now we have to wait. The next step is to take out the coin and clean it. And as you can see now, the coin is now a silver-colored coin. So, the result was a coin with a silver color. The silver color isn't silver, but it's zinc. So, what has happened during this experiment, I want to demonstrate you on this screen. So, this is the copper coin with the copper atoms, and we tried to make a layer of zinc above on these copper coins, like this. And the only reason why this happened was because we used sodium hydroxide and we used high temperature. So now you can see a layer of zinc and a layer of copper. So the metals are not mixed yet, so this is not an alloy. We have to do something extra to make it an alloy. The process in which we create a layer of zinc above another metal is called galvanizing. So this is galvanized copper, which means it has a layer of zinc above on the layer of copper. So to mix the zinc layer with the copper layer, we have to use heat, because then the atoms start moving very quickly, and when they are moving very quickly they will mix. So we're going to use the heat of a burner, and we use the heat to let the atoms move quicker, and hopefully then they will mix. So now you can see a color change. You see, it's a little bit cold color now. So when this happens, you have to cool it down. And now we have a cold colored coin. We used heat, and that heat was used by the atoms to move quicker and quicker and quicker. And when they move quicker, they will mix. And then this will be the new situation. So here we have zinc atoms mixed with copper atoms, and this mixture is an alloy, and the alloy has the name brass. So we started with copper. Then we created galvanized copper, which means it has a layer of zinc on it. And then we create an alloy, which means the zinc atoms and the copper atoms were mixed. And this alloy has the name brass. So the right answer was B, silver.
Okay, so what was the answers from our audience? Can we see it? Or, yeah, B, A, D, B, C. Okay, so many answers, but some of them were correct, some of them not. Yeah.
Nice.
Okay. Mark, it was amazing as well. So many layers. My question is, are they stable, these layers?
And that's a very good question, because the medals used at the Olympics was more or less the same mixture, brass. There was one element extra, but those medals have it's called bronze disease. So that means that after a while they change color. So that's a bit of a problem with this alloy.
Mm-hmm. Okay. And do you usually do this experiment with your students?
Yes, normally I do. When they are 14, 15 years old, when I practice my information about metals and alloys, then we will make our own alloy. Yes, so we do this experiment every year. Yeah.
Mm-hmm. So I guess they like these experiments, do they?
Yeah, a lot, because I also tell them it's not allowed to change money, because our state is owner of this money. So what we do is a little bit illegal, and everything you do what is illegal is always fun to do. So my students love this.
Yeah, I can guess. Okay, so thank you very much, Mark. And I can see that we have some reactions from our audience. Very nice experiment. Thank you. Cooking show. Yeah, of course. Yeah. Okay, so thank you very much again, Mark. And if there are no questions on you right now, so then we will see you in the final discussion. So
Yep.
thank you and bye.
See you then.
Okay. So now this was Mark, and now we are coming back to the Stuart's video. Maybe we can show up the question again. How to achieve 4 liters each in an 8 liter and 5 liter container. Do we have any answers on these questions? Okay, I have the reaction that we have no question. So then we can move forward to the second video of Stuart. So please pay attention and watch this video carefully.
So, welcome back. I wonder how you went trying to solve that problem. Did you manage to find a way to get 4 and 4? That particular problem you can solve. So let's see one way of doing it. I'll just have to see if I can remember which sequence is the solution for that. So I will first fill up the 5. That's about right. So I know I've got 3 here. I'm now going to pour the 5 into the 3. So now, even though I don't have a measure on here for 2, I know I've got 2 liters in here. So it was full at 5, I've taken out 3, I know that, I'm left with 2. I'll put the 3 back into the 8. And I've got 2 in here. I'm going to pour the 2 into the 3. And I know it's 2. 2 into the 3. I'm going to fill up the 5. Which is all good. Now I know I've got 2 here, and they've got a 3 mark, and this is 5. So if I top up the 3, I was at 5, I've taken out 1, I'm at 4. So I've got 4 here. That's part of the problem. I've got 8 overall. So I know I've got 1 back here, so if I pour this in, we've solved the problem. So I've got 4 and 4. So that's solved one problem. But is that the only way of solving that problem? What if I'd asked you to arrange to go and have 1, 3, 4? That would give us 8. Is that possible? How would you go about solving that? What about 3, 2, 3? Would that be possible? I could come up with a very large number of those sorts of questions. Would you have to try and solve this the same way each time? Trial and error? Can you tell before you start if it's possible? That's what I want you to think about, and we'll come back a bit later on in the stream and we'll show you a different way to think about looking at this problem. Best of luck.
Okay, so this was the second part of the Stuart's video, and it was kind of mixing waters. But nevertheless, now we have our Adam here. So welcome, Adam.
Hello, hello.
How are you?
Yeah, I'm great.
How are you feeling?
Yes.
Fine.
Yeah, fine.
Adam, to be honest, this is our first time in front of the cameras and speaking English.
Like together?
Yeah, like
that's
together.
true.
So this is quite amazing for me.
It is.
Yeah.
Truly it is.
Yeah, okay. So Adam, I know about you that you love radioactivity.
Oh, damn, yeah.
Yeah. So how did you came across radioactivity?
I think during my university studies, we was studying about radioactivity, of course. But I think that when I was working in Science Center, I prepared like educational program or lesson about radioactivity because we have a project about problems with space explorations, and one of the problems was focused on radiation. So then I just want to buy some Geiger counters and just try to measure radiation, and then it's just happens, and I have a large collection of radioactive stones and uranium and stuff.
Yeah.
So
I can remember that. Yeah. It's very interesting. Yeah. And I also know that you are traveling a lot regarding the radioactivity and regarding your teachers' school. So how many or where have you been to?
Like this year or in general?
In general, yeah.
Yeah, I was like, you can call it teacher in Mongolia. It was amazing experience, like few months. And also I was on a course for teachers, for physics teachers in CERN. It was a wonderful opportunity, and other travels as well, like in Turku on Science on Stage. It was amazing festival for science teachers. So it happened this year.
Okay. And can you also remember our joint trip to Sweden when you had your
I remember.
the measurements, what is called like
Geiger counter.
Yeah. And you had it at your plane.
Yeah, that's true. Yeah, I was trying to measure how large is the radiation according to the height, altitude, I think it's called. Yeah. And also, it happened that I measured also how the radiation change according how north are you also, because the north are you, the more north are you, the higher is the radiation as well, because of the magnetic field of the Earth, and in high altitudes you can measure that. Yeah. So I also measured this thing.
It was very interesting.
Yeah. Security guys don't like my devices, but
you're right.
It was good. After all.
Okay, so thank you, and now I will leave you here. So the floor is yours.
Yeah.
Good luck.
Thank you.
Bye.
All right. Bye. And we're gonna focus on radioactivity, as you can guess, and we're gonna make some radioactive battery here in our studio on this table. I have a lot of things here, but first, I want to ask a question, and the question will be here, maybe not, because we're gonna plug some LEDs to our battery, DIY radioactive battery, and the question is, how many LEDs will we light up with our DIY radioactive battery, with the stuff I have here? Yeah, not much is here, but Yeah, a lot of things are here, but in true. So let's start. If you want to make electricity with radiation, first idea you can think of is to build a power plant, nuclear power plant. It's here. Yeah, sorry. I wouldn't move here. So this is nuclear power plant, but it's quite complicated stuff, because there is a nuclear reaction. We already talked about nuclear reactions in nuclear reactor in our last stream. So if you are interested, you can watch that. And this nuclear reaction creates, or this energy, nuclear energy, is transformed to heat. And this heat is transferred to kinetic energy, to movement. And this movement is transferred to the electricity. So it's quite complicated, a lot of stuff, a lot of steps. And if you want something easier, maybe you watched some sci-fi, Martian. And in Martian, you can have a movie scene like this. And the guy, Matt Damon, amazing Matt Damon, had the idea to take this thingy, it's not reactor, it's a radioisotope thermoelectric generator, and to warm up himself. And it's also kind of easy, but you need a higher radiation for that. And the principle is, you can see here, I want to change the picture. It will be here. Yeah, because you have a radioactive sample, and this sample creates heat, and this heat you can transfer to electricity. So you are out of one step, but it doesn't have such a power, so it's not. And you need a higher radiation doses, so, which is not that nice. You can call it like that. So we want to try something maybe easier and also safer. So we're gonna create our radioactive battery. And this year in September, in a science journal, Nature, if you read that, you came across to this article that some Chinese scientists make a nuclear battery. And it's really easy to understand. The principle is, it's really simple. And now you can discover that even a science journal, you can read it yourself and you can understand it pretty much. Yeah. So here is the battery. Maybe it will show up here. Here is the battery itself. So it's interesting, and you can see that there is a little greenish color, greenish light coming out, because this battery has 3 steps. We can put it out, and first layer we need to do this battery. It's to have some radioactive sample. In this radioactive battery, the americium-243 is used. This is not americium-243, it's 241, but it's americium. And this little metal is radioactive, and it emits alpha particles. Maybe you know this because this was used in old smoke detectors. In some countries, it's still in use, but not in EU. So this is quite old. And you can see that it's radioactive and it emits alpha particles. I need a camera, my radioactive camera, because this is a detector. And I want to show that it's radioactive. Aleš? Yeah, Aleš, this is a screen of our special camera, our special detector, basically. And now all these white dots are radioactive alpha particles, basically. So it's radiation. So you can see that it's pretty hot, pretty active. And this is our source of radiation. And the second layer, which we need to create this kind of battery, is to have some kind of scintillator. So the scintillator is basically a luminescent paint, luminescent layer, you can call it like that. And you probably know that if you have some stars on your ceiling or on walls or some signs of emergency exit, you probably know that. That's the same material, and if you shine a light on it, you can see the light. Yeah, it's a little bit obvious. Yeah, it's a little bit lighter. Yeah, we can do it again. Yeah, it's a little bit. Yeah, I can see that. You can see that. I can see that. So you probably see it as well. And this light, we're gonna transfer again. This light will help us to create electricity, and with pretty much easy solution. You probably know that the photovoltaic panel, the photovoltaic cell. This is it. And if we shine light on it, thanks to photo effect, discovered or described by Albert Einstein, we can generate electricity, some volts. Now we are generating we are creating 1.5 volts of voltage. So it's like a AA battery. Pretty simple. Okay, and now we can create our battery because we have all things, all the layers we need. But for the radiation source, we combine the first layer and the second layer, the radioactive material, with the scintillator one. And you can find in a store something like this. This is tritium like keychains, and it shines in the dark because there is a radioactive substance, tritium, which means it's a super heavy hydrogen, which means it's hydrogen with 2 neutrons in the nucleus. And if we dim the lights a little bit, can we dim the light? I need to turn off the light, all the lights, because this is quite a delicate thing, because it's not that easy to see the light. Oh, yeah, we are in darkness. And if we try our best, we could see, yeah, here it is. This is our phosphorescent plate. And here we can see some light coming out. It's not that bright. It's real gentle. The light is really gentle. And this light, we're gonna try to transfer to electricity, thanks to our photovoltaic cell. So this was just to show you that true little light coming out of these little glass tubes. And now we can turn on the lights again. Sorry guys, everyone in our studio. So I'm here again, and we need to put it to the reference. So we try to put our photovoltaic cells to darkness, to put a dark box on it. And now you can see how much voltage do we creating with photovoltaic cells. Not much. Yeah, it's like, now it's in millivolts, which means it's like 10, 11, 12, something like that millivolts. It's not that great. Yeah? It's not that great. So we are gonna put our radioactive samples on the top of the photovoltaic cell. And maybe we first, I'm gonna show you that this is really radioactive. So I need also, again, our detector, Alesh. Yeah, Alesh is my helper. And if I put the detector under these keychains, you can see the little dots. It's not that large because this is not alpha source of alpha radiation, but it's source of beta radiation. And this thing we see, it's not even a beta radiation, it's electromagnetic radiation. Cool question is to answer why there is electromagnetic radiation instead of beta radiation, but we're not gonna cover it right now, maybe in a discussion later. But it is radioactive. This is something what we saw. And now we're gonna put it on the top of our photovoltaic cells. So this is basically our battery, as was described in a Nature magazine. Radioactive stuff. There in the ampules, there is also a scintillating layer, luminescent layer, you can say, and then there is a photovoltaic cell. And if we cover it and we wait a few seconds, you can see that we are generating amazing 53 to something like that millivolts, which is maybe not that amazing. So now here comes the time to your answers. How many LEDs could we light up with this battery, with our DIY battery? Do we have any answers? It was more like a guess, I could tell you, but we don't have any guesses. No problem. I can tell you right away that we cannot light up any LED with this, because normal LED needs some units of some like 2.5, at least 1.5 volts of voltage, and this is not even close. So we need a large battery. And even the battery described in a scientific journal, in the Nature journal, produced power of the 70 microwatts, which is not much. You need a lot of them to power something up, even an LED. So it's not that powered. And the last thing, I have a last question to you, just to make a little bit of discussion. If you get this battery, what would you use it for? Yeah, if you get it, because it has some benefits, because the americium, half-life of americium, which is used to power this battery as a source of energy, is some thousands of years, which means that this battery could run your entire life, basically. And the later use are not that useful for you, but for some discoveries, it could be, or explorations, it could be beneficial to have this long life battery. So what could be your usage of this? And for the last thing, I can give you a hint for teachers, for example. If you want to make your own scintillator, it's kind of easy thing. The hardest thing is to get a radioactive source, basically. But if you have an old smoke detector, there is a radioactive source. But I must warn you, don't disassemble it, because it's not wise to do that. So it's up to you, basically. And if you take zinc sulfide, which is a pigment used in epoxy resins to make a nice glow with epoxy resins in the dark, and if you have a little piece of duct tape, where's my duct tape? Yeah, a little piece of duct tape. You will put a little bit of the powder of zinc sulfide on the duct tape, and that's it. You have your own scintillator. It's kind of easy to make, kind of cheap. This is mine. And if you put it on a source of radiation, and if you are in complete darkness, you can see light. But you need to be in the darkness for some while. So I make a photograph of the light. We can show that. The last question, last picture number 7, it is, I believe. Or not? Yeah, here it is. These are 2 pictures. The picture on the downside there is when I have red light turned on, and if I turn light down, you can see the light, even with your naked eye. This is a picture made with my iPhone, with my phone, with a 30-second exposure. But you can see that even with your naked eye. It's amazing. It's amazing to see the glow of radiation which you create. And this was our last thing, to little experiment you can make yourself if you got some sources, like radiation sources.
Okay, so this was Adam's performance. Thank you very much, Adam.
Yep.
I think that it was very amazing and interesting. And I think that in general, radioactivity is a very interesting phenomena, but it's not very easy to understand it, yeah?
Yeah.
Like for me, for example.
Yeah, it's not.
Yeah.
It's really abstract. You cannot see that. And everything you cannot see, it's a little bit challenging to understand.
Mm-hmm. Okay, and I have just one question on you. What would you use the battery for?
For battery for
you
personal? I was thinking something, because I saw on YouTube that some craftsmen on internet craftsmen, make such batteries to power a calculator. So that's
interesting.
It's amazing. You can find it on YouTube. I think oldest video is like 8 years old, so it's not that new idea. But with americium 243, it's quite new because it's a long time. Because half-life of this tritium is something like some years. I think it's like 6 years or 7. I'm not sure, but it's something like that. Yeah, approximately.
Okay.
So it's not that life thing. It's not that long. The life of the battery is not that long as with the use of americium.
Okay, thank you. And do we have some answers to Adam's question? Can we see it? Sorry again. Is this type of batteries future of energetics?
Oh no! I think that because the power it's laughable. It's nothing really in energetic. But maybe for some space research, space exploration, you need to have some reliable, lifelong batteries or source of energy. So this is the usage. I think it's good to have something like this.
Okay. Any answers or reactions on Adam's performance? All clapping hands.
Thank you. Yeah. Isel.
Does Adam have kryptonite?
Kryptonite, of course.
It was a really fast answer.
It's called uraninite, and it's a uranium ore.
Okay, and maybe I have one question on you. When you showed us those little stuff you have here, where do you usually buy them?
Like this thing, it's normal to buy. It's not that cheap. It's cost €2. In Czech crown, it's like 500 crowns. You can calculate it yourself. And the other thing, like the smoke detectors, I found something on old fabrics, not fabrics, old like workshops or old factories. So I found some of these there, and that's something, because you can find something like antique things, but nowadays there is not much things which are radioactive, which is good. Yeah, really, which is good. But the few legal things you can buy, it's this thing. Also, welding rods you can buy, with thorium, and in some parts of the world you can still buy the smoke detectors, but not in EU. It's illegal to use them in EU.
Okay, so thank you very much. If this is all from you, I would like to thank you again, and let's move on.
My pleasure.
Okay, so here we are again, And I got a message from our backstage that we don't have any answers to the second video of Stuart. So we will smoothly move to his third video. So let's get started.
And welcome back. I wonder if you've made any progress thinking about a different way of solving this problem. Hopefully you didn't just run to Google or ChatGTP to go and look for answers. I'm always interested in trying to solve things for myself first. One of the things which we as people face when we try to solve problems is our history, our evolutionary history. So for most of our existence, we've been very visual creatures. We're scanning the environment for food, for mates, for threats, for safety. We're very visual, and we kind of remember things in a visual way. We kind of develop maps and ideas about how to get from one place to another. It's only been more recently in human history we've had kind of abstract ideas, things where you might have a sequence of events that I need to do this process, then that process, then this process. That's a much more recent challenge for humans. And so in our brains, we have an enormous amount of our brain is devoted to working visually. We've got a much smaller part of our brain available to go and solve those problems where we have to think into the future step by step by step. This problem is one of those kind of step by step by step in the future problems. But if we want to, we can actually change that and think of a visual way, not just seeing the water pour, but we can think of a visual way to represent the problem. And that's what I'll share with you now. Here is a simple grid. It's really a graph of our jugs and the water. So here I've got our 5-litre jug, and this represents how much water is in the 5-litre jug. And down here we've got our 3-litre jug, and we'll represent how much water is in the 3-litre jug. We don't have to worry about representing the 8-litre jug, because if we can show all the water in the 5 and the 3, we know what's left is in the 8-litre jug. So when we think now about the problem I gave you, we need to get to the point where we've got 4 litres in the 5-litre jug and nothing in the 3-litre jug, because we want 4 in here and 4 in here. So on this grid, on this graph, this is really where we want to get to. We want to get to this place. That's the answer that we're looking for. And we start with both of the 3 and the 5 empty. So we start with 0, 0 down here. So the way we use this graph to go and solve the problem is if I pour water from the 8-litre just into the 5, I have to keep pouring, 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 and we're adding water. But I can't stop here because I don't have a 3-litre mark on the 5-litre jug. I can't stop. I'd be guessing. So if I pour water in, I've got to go all the way up to the 5. That's where I can stop. So that doesn't give us the answer. But if I pour from the 5 to the 3, I can represent that on the graph. So as the water comes out of the 5, glug, 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 the water in the 5 will go down, the water in the 3 will go up. All right, so 3 is at 0 at the moment. So let's pour water out of the 5 into the 3. So the 5 goes down, the 3 goes up, and we keep pouring until our 3 is full. So our 3-litre jug now has 3 in there. So I can think about those changes looking at this grid. I can go up and down, pouring in and out of the 5. I can go this way and that, pouring in and out of the 3. I can go this way, pouring between the 5 and the 3. I can't go this way on this grid because that would mean both jugs are filling up at the same time. And I can't pour from the 8 into both jugs at the same time. Doesn't make sense. So now what we can look at is, how do I travel around this grid to get to here, to stop there? And I can stop here. I can then pour over here. That's emptying the 3 back into the 8. Transfer from the 5 to the 2. Fill that back up. Pour a bit over and then empty it out. And I arrive over here. And so it's a bit like playing a game of pool. How do you bounce around off those edges, or reflecting beams of light off mirrors? How do you bounce around to get to here? And we can see with this, it helps us understand something special about all of these kinds of problems. You can never stop here. You can't stop pouring halfway through. You've either got to stop at the top, or when one is empty at 0, or one is full. And so if I asked you, can you have a pouring which gives you 1 litre in the 3, 3 litres in the 5, and 4 litres in the 8, because that's what's left. 1 plus 3 is 4. 4 would be in the 8. Can you arrive at that point? It's impossible. You can't get there with this challenge. And so all of these are impossible. You can't do that. And I don't even have to try. I can just use this way of looking at the problem now to go, that's impossible area. We can land on all of the edges, but we can't stop in the middle. So hopefully that's given you, one example of how you can look at a problem in a different way, how you can visualize a problem. Now we can ask lots of questions about that, and we can have a different understanding. So hopefully that's given you some experience about how some ideas in science can really transform how we view one simple problem to give us a tool to go and answer questions in many different areas. Hopefully you've enjoyed that. Thanks very much.
Dear audience, this was our last video from Stuart. I hope that you have a lot of questions, but unluckily we don't have him online. We can't ask him right now. But if you have any questions on him, just put them in comments and maybe we can send him the questions from you. But now we are quickly moving to Bhutan, our last stop. Hi, Sobit.
Hi.
Can you hear me and see me?
Yes, I can hear you.
Perfect. Okay, so welcome to our stream. I have to say that you are a very brave man because many of audience doesn't know that you have a late night right now. What's the time?
At the moment, it's 1:45 a.m.
Okay, so I guess you are not going to sleep right now.
No. The amazing experiment kept me awake. Yeah.
Okay. So before we start with your presentation, I have some questions on you. As I said, you are from Bhutan, and I looked on a map, and I see that Bhutan is quite a small country with a small population. And it is also situated right under the Tibetan plateau. So it's quite very hilly. So what is the life like there? And what is the science like there?
Okay. Yeah, you're right. Bhutan is a small country and it's like situated between the two giant countries like China, India, and our nearest neighbor is India. Uh, we in the past we were quite isolated, but we were taken to the world through our king's vision, and at the moment we are known for gross national happiness, which was uh, coined by our fourth king, which basically talks about that not only the money, not only the economic growth, even the spirituality, there should be a balance between the ecological conservation and also the economic growth. And recently, our present king, fifth king, have introduced Gelifu Mindfulness City, which is a long-term vision through which our country is now known to the world more, and more innovation is coming up. And through this mindfulness city, it's going to be a urban hub for the Asian countries as well as the all parts of the world. And basically, the science out here is that like 3 years back, space exploration has started in a small way. Bhutan 1, our nano satellite, was launched. Second satellite was launched with India, and the third satellite, nano satellite, is coming up in the next year. So we are quickly moving forward, and yeah, that's it.
Okay, so great to hear from you. So do you feel more happy and free?
Yes, I feel happy, and I'm fortunate to be born in Bhutan. Being a Bhutanese gives me great happiness. We are known to the world as one of the happiest country in the world, and we are. We value spirituality and helping each other, uh, fulfilling the greater responsibility as a citizen, that is to make the country great, help each other. So in a way, it makes us proud, and we are very much we regard our king almost like our god, because uh, he has been our role model. Yeah.
Okay, I can see. So like you. And
Yes.
I can also see that you have some kind of national dress on you. So
Yes.
can you
Yes.
please describe what kind of clothes is it?
Okay, it's called Go. For male, we wear Go, and for women, they wear Kira. So basically, there are many types of Go, like Mata, Seta. So this is one of them, like cotton made and all. So many types of Go are there, and even the Kira. And especially for this special international event, I thought of wearing my national dress. Yeah.
Okay, it's very kind of you. So
Yeah.
let's leave the floor for you. Good luck.
Yeah. Thank you. Okay. Hi, everyone. So today I'll be doing the presentation on our walking prototype known as mindful driving, which is a smart technology for safer roads. So this working model we presented in our STEM exhibition that was on November 11. So November 11 is the day when we celebrate the birth anniversary of our fourth king. So the theme was Innovate for Tomorrow, Shaping a Sustainable Future. And uh, we stood second position in the district level. Before I start, I'd like to present you with the question. If I can have a first question. Yeah. So the first question is, what two major issues does the mindful driving model aim to address? So can I have the options so that the audience can just guess what I'll be talking about? So dear audience, you can go through the 4 options and you can type what my project, my model is going to talk about. Overspeeding and reckless driving, traffic congestion and vehicle maintenance, driver fatigue and alcohol consumption, and poor road condition and navigation errors. Okay, I can see some of you are writing the options. Okay. Okay, good to see some of you are right. Okay, thank you for the response. Now, I would like to start with the video first. Okay, can you pause a bit? So, for making the model, we went through phases like planning. Then our students made constructed the base of the model. Then this is called as Mani Dunkor, spiritual thing, and then we construction of the road, building of the car body, and this then the students were asked to make the model such that the car can move in a circular motion, and there we went through a lot of trial and error method. At first it wasn't working, but through lots of trial and error we finally it worked. And we can see here the car, I mean, it is moving perfectly in a circular motion. We did circuit connection. There was testing of the alcohol sensor. So this is the testing of the alcohol sensor, whereby when we bring alcohol near to the sensor, it detects. So as you can see, this is the RD. So through this, if it goes alcohol value goes above threshold level, then the car stops. So in brief, this is how it works. Then the next was eye blink sensor testing. Then the motor car, and this is our model, mindful driving, and we have some quotes pasted on it. And this was during our STEM exhibition. So as you can see here, the car is moving perfectly fine. So at this time, but you can see the car has stopped. Now this one, you can see here, as the car is moving, it stops because the driver has fallen asleep, and it detects that the driver has fallen asleep, and as a result the car stops. So in brief, this is how the model works. Can I have, yeah, this is the one. So you can see here, when the you can see when the driver wears these goggles with the eye blink sensor, if the driver, after a long journey, long hours of journey, he gets fatigued and he feels asleep, then what happens is the car stops, the buzzer makes noise, and you can see the water coming, splashing his face, his eyes. So as a result, the driver can gain his consciousness. You can see my student that on his face the water is splashing. So that's how it, in brief, it works. Okay, thank you. Now let's move to our PPT. Okay, so before I begin my PowerPoint presentation, the theme was Innovate for Tomorrow, Shaping a Sustainable Future. So taking the inspiration of our vision, gross national happiness, and mindfulness city, we thought of making innovative project whereby the main aim was not only to win the competition but to engage the students through hands-on activity to make them know some of the science concept, physics concepts such as electromagnetism, infrared technology, uh, and relay, and so on, as we and even the coding. And here we our HM has time and again mentioned that STEM should be the universal language, especially for the youth. So I found that through this model, in a way, student could learn all these new concepts, and as well as they could inculcate the 4 C's, that is the critical thinking, collaboration, communication. So in that way they develop all this skill. Okay, now I proceed. So this is the brief circuit connection of the alcohol sensor. So this is your Arduino Uno. This microcontroller, a brain of this circuit. And to this Arduino Uno, alcohol sensor is connected. And so this alcohol sensor, it has some parts like VCC, analog signal, GND. So VCC is voltage common collector. Then we have AO, analog output, GND, ground connection. So here, how the connection was made is the VCC of the alcohol sensor. By the way, this alcohol sensor is called as MQ3. So the VCC of MQ3 is connected to the 5 volt of Arduino, and through Arduino it gets its the voltage. Then the ground of MQ3 is connected to ground of the Arduino, and analog output is connected to the AO, analog output of the Arduino. So this is a short brief connection of the alcohol sensor to Arduino. Now, our model does not only talk about the alcohol detection, but also about the there are many other parts. And from here, now we are connecting to the relay. We need a relay. Relay is like automatic switch. So first we have 2 relay. So the first relay was used for alcohol detection control. So the VCC of the relay, just like in alcohol sensor we had VCC, similarly relay also has VCC, and this VCC is connected to 5 volt of Arduino, and GND is connected to GND of Arduino, and there is signal pin of the relay which is connected to digital pin 9 of the Arduino. Now this is the brief circuit connection for the eye blink sensor. So the earlier one till this much is for alcohol sensor circuit connection, and this one is for the eye blink sensor. At the moment, I'm just talking about the input part, and later on I'll move forward to the output part. Now this is called eye blink sensor. So eye blink sensor, it has IR emitter, IR sensor, and it also has VCC, GND, and output pin. So here also the VCC of this eye blink sensor is connected to the VCC of the second relay. So here we are using the second relay. The first relay was with the alcohol sensor. So VCC of the idling sensor is connected to the VCC of the second relay, and it is also connected to the positive terminal of the battery. Now the next is ground part of this idling sensor is connected to the ground part of the second relay and the negative terminal of the battery. And the third one, that is signal pin of this idling sensor, is connected to the signal pin of the second relay. Now this till this much is the input part. For the first one is the alcohol sensor and the second one is the idling sensor. Now the output part is the COM. In the relay there is a pin called common part. So the common part of both the relays, it is joined together with the wire and it is connected to the first part of the switch. Then from the second terminal of the switch, it is connected to the positive part of the various component like our buzzer, water pump, LED bulbs, and the positive terminal of 3.7 volt battery. Then in the relay, there is another point called NO, that means normally open. So the normally open part of both the relays, it is being connected to negative part of the water pump, LED bulbs, and the negative terminal of car motor. And at last, after this connection, now to make the circuit complete, at last is the negative terminal of the battery is then connected to positive terminal of the car motor. So you might be wondering, in the beginning I showed you the video whereby the car, it started running smoothly, but if let's say the driver has consumed alcohol more than required, more than the threshold level, what happens is the car stops immediately. It won't start only. So how is the alcohol sensor working? So now I'll talk about the working principle. Okay, so this, anyways, so here the alcohol sensor, it works by measuring the change in the resistance of an internal sensing material when exposed to alcohol. So here this alcohol sensor is made up of a semiconductor known as tin dioxide. It has a layer of tin dioxide, and what happens is oxygen, if the air is clean, the oxygen will get absorbed into this tin dioxide layer and thus attracting electrons, and as a result there will be barrier, there will be resistance, and as a result the current won't flow. But when there is alcohol in the air, then what happens is this alcohol will react with the oxygen, and this oxygen, when it gets contact with the tin dioxide, then what happens is it reduces the resistance. As a result, the electron flows, the current flows in the circuit. And that's how when we bring the alcohol near the alcohol sensor, it detects the presence of alcohol. So if the alcohol sensor detects alcohol, which is, let's say, above the certain threshold level, then what will happen is our Arduino, our microcontroller, it will get triggered. It knows that the threshold level of alcohol has reached, it's more than that, and as a result it will pass the message to the first relay. And when the first relay gets activated, then the normally open, the NO, that's normal open, contact remains open, and since the circuit gets open, the motors, it cuts off the motor's negative connection, and that prevents the motor car from running, meaning the car stops. So this is how the alcohol sensor works in preventing accidents. We know that it is said that one of the leading cause of accident is drunk driving and the driver fatigue. So this is how we came up with the idea that through using this alcohol sensor, we can prevent, in a way, accident. Now, this is the coding, Arduino coding. So here, this it's called a software called Arduino IDE, and here basically this coding has it talks about the alcohol. We have at first threshold level we kept it as, let's say, 850, and here when the alcohol value is greater than 850, then what happens is it has reached its threshold level. So as a result, alcohol is detected, then the motor stops. And if it is below the threshold level, then the what happens is the car keeps on running. So this coding for this setup. Now, before I move to the eye blink sensor, I have one question regarding the alcohol. If you can highlight that third question, it is about alcohol. Yes. So how does the resistance of the alcohol sensor changes when ethanol is detected? So, dear audience, what do you think? Will it increase? It decreases, remains constant, or fluctuates randomly? So, okay. So, audience, you can give your answers. What could be? Okay, one of you have answered. Okay. Yeah, that's good. I can see many of you are giving the correct answer. It's nice. So the correct answer is it decreases, option B. Thank you. Now, let's move to the second part. So, in our model, we made use of ethanol, ethyl alcohol, since it was present in our chemistry lab. And when it reached above the threshold level, the alcohol sensor detected and the car stopped running. Okay, now let's move to the eye blink sensor. So the eye blink sensor, main thing, the working principle eye blink sensor is it is based on infrared technology. So basically, eye blink sensor, it has a sensor, IR transmitter and IR receiver, or you can say IR emitter. It emits that infrared light. So infrared light gets inside our eye, or it scatters to our eye. So imagine the infrared light getting inside our eye. So I'm opening my eyes. Now when I open my eyes, then what happens is sorry so when the infrared light gets towards our eye, if the eye is closed, then what happens is the eye rays will get reflected back with larger intensity. It gets reflected back with larger intensity when I close my eyes, and that will be detected by the photodiode. Now if I open my eyes like this, then what happens is obviously IR light will get emitted to my eyes and scattered towards my eye, but it will get reflected back towards the photodiode with less intensity. So you can see there's a fluctuation of the intensity when reflecting back. So thus, if the sensor detects our abnormal eye blinking, it indicates drowsiness, and it will then trigger our second relay. And this the second relays, it has a normally open part. So this contact is connected to the negative terminal of the motor. So when the relay is triggered, saying that the relay gets triggered because it has detected the abnormal blinking of the eye, drowsiness. So what happens is it opens the circuit, and thus the car stops. So that's how the eye blink sensor works. Now the last one is relay module. Now this relay module, throughout this experiment, we have made use of relay module for first the alcohol sensor, and the second one is for the eye blink sensor. And relay module plays a very important role. Its main working principle is actually electromagnetism, and we teach students about electromagnetism, and through this module they learn better about electromagnetism. So inside the electromagnetism there is a armature coil. So when we apply voltage through battery to this relay, then what will happen is the coil gets powered, it gets voltage, and this current will produce the magnet. So what you call the production of the magnetism through current, we know that's electromagnetism. And as it produces magnetic field, it will help the armature coil to move to close, and as a result, this you can see these two point, it gets attracted. So it gets attracted. So as it closes, the bulb glows. So you can see here the bulb glowing. So which means the circuit gets complete. So this relay, in a way, it's act like an automatic switch, is act as a circuit control. It allows a low power signal to control a high power circuit. So this is how the relay module works, and its principle is known as electromagnetism. Now, what are the features or the advantages of a working model? Number one, enhance road safety. Yes, both by using alcohol sensor as well as the eye blink sensor. In a way, it helps in preventing drunk driving and drowsy driving, reducing the risk of accidents. And moreover, in our system, the interesting thing is when the driver falls asleep, and when the driver falls asleep, and if his eyes remain closed for like 2 seconds, then what will happen is the eye blink sensor detects, and as a result the car stops. Not only that, there is a buzzer also. So buzzer makes noise, and in our car we also have put the LED bulbs in the front part and the back part of the car, so as to avoid accident. Because when the car suddenly stops, then there's chances that from the back part the other car might get crash to our car. So as a result, these LED bulbs at the front and the back, it will also help in preventing the accident. And at last, the interesting thing about our model is that when the driver falls asleep, then what you call the water also splashes on his face. Thus, the driver gains his consciousness. And it also has sustainable impact, like it reduces material waste and carbon emission by preventing accident vehicle damage. And moreover, uh, it aligns with the sustainable development goal, like safety, like health, transportation system. And the last is versatile and scalable. It can be implemented in the commercial, personal, or public vehicle, especially not only traditional vehicle, it can also be used in electronic vehicles. And in our countries, there are some electronic vehicles as well. So maybe in future it's possible that integration of this sensors such as alcohol sensor, eye blink sensor can be helpful in preventing this road accidents, and in that way we can save a lot of life. And this is one of the real so I saw this in one of the YouTube videos whereby they have come up with a prototype. And so in our prototype we have made use of alcohol sensor, eye blink sensor and all. And in reality, if we integrate into our vehicle, then we can integrate in this, for example, like this, in the what you call car steering. And also we can keep, let's say, vision based alcohol detection. So I saw that in some of the developed country, they have come up with this vision based alcohol detection, whereby the driver is inside and there they have some kind of camera that detects whether the driver has consumed more level of alcohol. So in a way the car automatically stops. So that's all. Now I would like to conclude here. So here we have one more question. Can you show question number 2? Okay, what does an eye blink sensor detect? So audience, is it air pressure, infrared light changes, sound waves, or brain activity? Okay. Okay, yeah. Looks like all of you listened carefully. All of you gave correct answer. That's infrared light changes. So I would just like to conclude here that this working model is, I mean, it's just a prototype, but it has some potential. In future, maybe it can be made into real life application, and maybe in Bhutan also, since we are coming up with the Galifo mindfulness city. So maybe in future we can have such kind of vehicle whereby all these kind of sensors are used, and in a way it can help save life. That's all. Thank you.
So thank you, Sobit, for your presentation. I have to say it was very amazing and properly prepared. So thank you again.
Thank you.
And
Thank you.
yeah, we have some reactions, so maybe we can show them. In Bhutan, people drink alcohol.
Yeah, some trick, but I don't. Yeah.
Okay, nice model. How long can the car go around?
Like in our working model, we tried in the beginning. It didn't move properly, so we had to work like trial and error method again and again. And when counting, it moved like more than, like, for example, 30 times. Like it made a perfect circular motion. So this is just a prototype, but in reality, obviously, I think it can cover more kilometers.
Interesting, yeah. And we have some reactions. What a very good project. Respect from Mark Bet.
Thank you.
So,
Thank
yeah,
you.
and I have to say that when I saw for the first time the model of the car, yeah, I was thinking that it's just quite simple, but with all the wires and sensors and batteries inside, it seems very sophisticated one. What do you think?
Yeah, yeah, it is. So actually, we took like almost like 1 month. Right after the class, we used to walk sometime even night with my students, and it was also a learning experience for me. Sometimes it worked, sometimes it didn't work. So a lot of trial and error method went, and we are. I mean, in the end, we in a way secured second position in the district level. So it was quite a proud moment for me, for a student, as well as the school.
Yeah, I can see. And just one question, where did the initial idea of this model came from?
Yeah, so basically, as I mentioned earlier, especially this year, our HM, His Majesty, has talked about the Galifu Mindfulness City. So with that thought in the mind, so that would be it will come into reality. It will take like almost like 10 years. So we discussed, we in the first video, I asked, you can see the students planning. So we discussed that, think of some idea, whereby we can in a way maybe bring changes, and we want to see in the mindfulness city. So taking that into consideration, we came up with the idea. And one thing I want to tell is, in our model, we have balanced both the economic and the spiritual aspect. In the middle, you could see that spiritual thing, Manidunko. So in Bhutan, it is ritual, it's traditional, whereby people rotate. So that's how we wanted to show spiritual aspect as well as the scientific approach. And that's what the mindfulness city and our country's vision of gross national happiness emphasize on. Yeah.
Okay, so this is a great idea, and it perfectly fits. And I can see that we have some reactions from our audience. So, wow. Can you read it for us?
Yeah. Okay. Namisameka dinchila. Okay. Thank you.
What does it mean?
It means thanks a lot. Yeah. That's what it is.
Okay.
Thank you so much. Yeah.
So thank you, Kakarinka, for this reaction. Awesome, Sobit. So thank you.
Thank you.
Another reaction. Excellent project. Okay.
Thank you so much.
Okay, Sobit, thank you very much. And we will see you in a while in our final discussion. So now let's move on.
Okay.
And now we are moving to our final discussion. We will see our guests online. So let's have a fun with final discussion. Okay, so we are heading for the final, but before we have some discussion, we might need some questions on our guests. So don't hesitate and feel free to put some question on our guests, or maybe guests can ask each other. So just feel free to do it. And meanwhile, I would like to invite you to our next stream, international stream, which will be held next year on April and on the 29th of April. And as you can see, the topic will stay the same. So Science Today, because we think that this is really up-to-date topic, so we can talk about the science of today all the time. So please put your questions and we can move to the final discussion. Okay, here we are. Can you hear me? Hi. I'm very, very glad that you are here with us in the final discussion. So how do you feel now? How did you like our stream or all the experiments? Who will start?
Shall I start?
Yeah, Sobit.
Since I was the last, I'll start. Okay. So you know that right now it's 2:25 a.m. But all of you kept me awake with amazing explanation, amazing experiment, and very unique. And like the first one, it was quite unique. And my student also joined actually. So all the experiment, I could learn a lot. Uh, I want to ask, like Adam, the radioactivity. So it's not an easy task, I mean, to use the radioactive material. Is there any like ethical consideration to take care to use this radioactive material?
Like with students or in general?
Yeah, uh,
Yeah,
in general.
yeah, in general. We can use some like uh, low doses of some not that radioactive materials we can use, like a general geological stuff we can use in schools in general. That's allowed because you cannot like ban to have a stone in your class. It's
Right.
impossible, really. But other things, like the historical things, like uranium glass or some radium dial watches, it's
Hmm.
like gray area. It's not. It is banned, but nobody cares. Yeah, that's the
Yeah,
thing.
yeah,
That's the
yeah,
idea.
for
If
learning.
you,
Yeah.
yeah, for learning purposes, you can bend it. Really, the law. And if you want to use like radioactive substances itself, um, it's denied. You cannot use them. You can
Okay.
use them for to such a level of radiation which is safe and it's defined by law, but it's easier to just deny it and don't use them that much. You can use the things which are legal to buy, like the thorium electrodes for welding or other thing. There are few things you can buy, like
Okay.
potassium salt, for example. It's a little bit radioactive as well, so that's
Okay.
good samples to use and safe.
One thing, with that small voltage produced by radioactive material, could it be used for like making pacemaker or something?
Yeah, maybe yeah.
I thought maybe.
I think it was used in history. There was some. I think in a Soviet Union there was a peacemaker with, I think, plutonium, or it was maybe just idea. I don't know if it was like tested and it was put it to the practice, but I think there was idea in the Soviet Union to make peacemakers with
Okay.
with plutonium.
Okay.
And basically it's because for old people you not that afraid to have a cancer, because this stochastic effect of radiation, you need a long exposure for a long time. So for older people it's not that harmful in a way, but still you are putting radioactive stuff to people, so which is not a smart idea, not the smartest idea, I think.
Right. Okay. Thank you.
Okay, so thank you, Sobit, for your question. And what about you guys? Do you have any questions on our guests? Or, oh, I got a message. We have a question from our audience, so please. I have a question for everyone. Will you anything use what you have seen in this stream? Like, I think that it is meant like from, for example, from Carlos when they saw the experiment from the other one. Will you use it?
I don't quite get it. So you mean so the
If
point is
you,
not.
yeah, if you will use any experiment you have saw in this stream for your own school classes or so on.
Teaching practice or just
Yeah.
a demonstration, like.
Well, as a demonstration, I like very much the one about the radioactive, because then you can also measure things. So well, I saw already your cloud chamber. I fall in love with it. So
Yeah.
now this is nice because you can. I am a physicist, so you can quantify. So you can somehow know how many voltage you can produce, and maybe you can put more, or I don't know how to, if you can excite the tritium in some way. I have no idea. But yes, it would be very interesting to test it. I will try to test it to buy this tritium stuff.
Okay. So, any one of you, or we have another question? Do you have any favorite movie about science, or where is science discussed, and what is it? Question from him.
Like one of my favorite science movie would be Interstellar.
Oh yeah.
I can agree. I can agree.
That is obviously
Yeah.
so many concepts are taught.
Yeah. Yeah.
Sure.
Any other ideas from you guys?
Yes, the Royal Institute has a YouTube channel, and they have very nice movies about physics, chemistry, science. It's very good.
Okay. And you, Carlos, can you?
I have to say, I love, I like a lot the science fiction. So it's not really proper science. So, but anyway, one thing I started to see the problem of the three bodies.
Oh yeah, the series.
Yeah. And the nice thing is that I did recognize the place they were filming it, because it was in exactly in ISIS, in the neutron source, not in the neutron source, but in the synchrotron. So I was like, oh, I was there. So it was very nice for me. It's science fiction, but to recognize a real science building in a movie, it was very nice for me.
Okay, interesting. Okay, we have another question from the audience. Petr Nekonečný is asking, how dangerous is Röntgen at the dentist?
Not much. It's
Too small.
If you compare it with all the radiation dose you get among the year, it's almost nothing. Not nothing really. You cannot be X-rayed every day, but once a year, two times in a year, it's not dangerous at all. Or it could be, because you cannot tell which radiation, which medical screening is the hard one. You cannot detect which radiation, which ray was that caused, for example, cancer or something. You cannot tell it. But if we are speaking about probability, it's nothing basically. Statistically, it's nothing.
And does it somehow differentiate the dentist from other medical doctors?
Yeah, it is.
Yeah?
Because for soft tissues, you need a larger amount of radiation. For example, mammographs, you need a higher doses. Or if you want to have X-ray of lungs, yes, sorry, I just clicked my microphone. You need a really high doses. And if you are on a CT scanner, that's almost like a year dose, or just one screening of CT.
Okay, so just going to dentist and having a Röntgen is not such a big deal, yeah?
Dentist is safe. Yeah.
Okay.
This is the lowest doses of all medical screenings.
Perfect. We have some reactions. The Kakarinka, I just want to thank you all participants and producers. You are great. Thank you. So,
and we are thanking you.
Yeah, thank you very much, Kakarinka. Okay, and maybe I have a final question on you, both of you guys. I'm just wondering, what does science means to you, like the science of today? Can you please briefly answer? What does?
Okay, I think I can start.
Yeah,
if I could.
Okay.
I think it's important to teach about modern science, like science today, because in school often we are teaching about stuff which is old, like about Newton and Pascal, about these great minds which were amazing, yeah. But the science is today, and it has its own discovery even nowadays. So I think we should, as a teachers, we should teach even the current science, what is happening right now. You can visit some place, you can visit some labs. It's always option in our country. I don't know if it's possible in other parts of the world, but in Czech Republic it's quite easy because we have labs in every large city.
Yeah.
So we can visit that and inspire students to give them some idea what is happening right now in a world of science. And with Sobit, we are on a high school program for high school teachers, and we was talking just about this, that we need to teach students about like nowadays science.
Yeah.
Right.
Mark, you wanted to add some point?
Yes, I think we have a lot of problems now in this world, environmental problems, energy problems, and I think that the answer will be chemistry, physics, science. So I think it's very important that we tell the story about science. Of course, we need to tell something about the history of science, but also about the future.
I have to agree with you, totally. So do we have any questions from audience? No.
I think we can let Sobit and Carlos answer as well. Yeah.
Sorry.
Oh, okay.
No,
So
I want to think about what science for me, first of all, is my job. So science is nice. It's getting a little bit crazy now. I don't know if you know the problem of publish or perish. So what we are constantly, we need to publish and it's getting a little bit crazy. So the romantic idea of science I had when I started my PhD now is I am a little bit like, okay, we should like calm down a little bit, because I don't have the time to let's say to have fun with. So I think it's getting a little bit crazy from one side, and from the other side, I also agree that science and the scientific thought based on evidence and not on opinions is extremely important, because what we are seeing now in politics, okay, I will not say, but is that opinions and evidence is at the same level, and no, evidence is here and your opinion is your opinion and it can be true or not. But if there is a global warming, you can measure it, and if there is a global warming, there's no discussion. So I hope that more than science, the scientific thought gets into the governments of everywhere, so that we can really talk about something that exists and not something that it's invented somehow.
Totally agree. Yeah. And Sobit, how about you?
Okay. For me, science obviously it's related to solving problems, current problems in the world, and apart from that, I feel that science it also help us to know about our life, how to proceed in life. We make better decision, and also for me personally, it has a connection with the spirituality. I especially like a lot of astrophysics concepts, and even while going to CERN, there we learned about the particle physics, and it's so amazing that the scientists are doing things like they are making what you call the machines which are able to see the unseen, kind of seeing the unseen, and that in a way made me feel like it's like connecting to the spirituality. So, and that's what makes me learn more about science. And back in my school also, I run STEM club, and I'm the coordinator, and I help my student to engage in this prototyping, so that the student can know more about the scientific things.
Yeah, this is definitely true. So thank you. Thank all of you for your nice discussion. And now I just feel that we are at the finish line. So let me thank all of you from the audience. You were great. Thank all our guests to be here with us. It's our pleasure. And as the final, we have a video from Mark. So now we will start the video, we will play it. So
for this experiment, we need a glove made of plastic, elastic, a balloon, something to make a drawing, scissors, vinegar, and sodium carbonate. First, you have to cut one of the fingers from the hand glove. So now you will fill the finger with vinegar. Stop. So then you will close it. Oh, so close it. And to keep it closed, we'll use a elastic. So, and then you will put some sodium carbonate into the balloon. And then you will put the hand glove with vinegar into the balloon. And now you have to close it. And if you like, you can draw a fish like this. So if you hit the fish, then there will be a chemical reaction that blows up the fish.
Okay, thank you, Mark, for your short video. It was kind of a pocket science, wasn't it? Yeah.
Thank you for broadcasting it. It's a very nice experiment. You can do with small children. You can do it in your classroom. No problem. Very nice.
Okay, so thank you very much again. And this is the idea for our audience. If you have some kind of pocket science like this, you can share it with us via our email. So let's do it. And now Adam has prepared something for us.
Yeah, also I have also pocket science with a fish, because always I bring with in my wallet this fish, this film. And if you don't know it, if you put it on your hand, it just starts moving. Just wiggling with the tail or with the head, or just fall down, whatever. And according to this little thingy, which is cover for the fish, you can tell a fortune. It is written here. That's if you are like in love or whatever. Yeah, it's nice. Okay. Or dead, it's also here. And it's a nice thing because it's kind of easy. It's very easy. And I use it with my students for teach them about scientific methods, because I give it to them and they are just making some fun with it. And then I ask them how it works, why it's moving, because obviously it's not about emotions or about fortune or whatever. So what is the scientific evidence behind the movement? And they are just trying to make some experiments and to discover why is it happening. And if you want to know what is the reason behind the movement, you can watch it on our YouTube channel. Yeah, it's already there somewhere. You need to find it.
Okay, is that all?
Yeah, it's everything.
Yeah.
It's everything.
So, okay, thank you. If this was everything, we are at the final. So again, thank you very much, Mark, Carlos, Sobit, and Adam. It was really my pleasure to meet you and to see all of your experiments and presentation. So thank you very much, and maybe see you next time.
See you next
Thank
time.
you.
Bye.
Bye-bye.
Thank you, guys.
Bye.
Bye-bye.
Bye.